Okay, I'm going to go through section 2.6 and 2.7. You can do the homework after you go through this. So here we're talking about what are called stem and leaf displays. So they look like like this. So what is this? So the way you read this is supposed to represent a set of data. Actually, it's supposed to represent this set of data, I believe. This is what the following are scores of 30 college students on a statistic test. So somebody got a 75, somebody got a 52, somebody got an 80, a 96, and so on. These are the scores. And I believe that this one is the so-called stem and leaf plot. So how do you read it? You read it like this. You say 5, 2. That means somebody got a 52. 5, 0. Somebody got a 50. 5, 7. Somebody got a 57. Is that true? 50. Yes. 52. Yes. I think the other one was 57. Yes. Okay, and so on. So how about this one? Somebody got a 65. Somebody got a 69. Somebody got a 61. No, that's wrong. Shouldn't be like that. Should be in order. As far as I know. Let's see. Is there a 61? Maybe it doesn't matter, actually. Maybe it doesn't matter. I usually assume that these numbers are in order, so the 1 should be over here. But it doesn't seem they're doing that. So 61. Is there a 61? Yeah. There's a 61. So I guess that's what it is. So usually they'd say put the 1 here, rather. But anyway, they're not doing it in order. Okay? So 65, 69, 61, 68, 64, and so on. Okay? So this is called the stem and leaf plot. So if you count, we said there were 30 pieces of data here that we were representing. So how many numbers to the right of this bar should there be? There should be 30. 1, 2, 3, 4, 5, 6. And if you count them all, it should be 30. Okay? So each one represents a score. Now, if you kind of rotate this counterclockwise by 90 degrees, then you get a kind of histogram, right? It kind of looks like a histogram. Do they do that? Let's see. Maybe not. But the idea is that, actually, that if you rotate it 90 degrees, you get a kind of histogram, so by making this picture, you can get an idea of how the scores were spread out. So you can see that since this is the sort of the longest, but if I rotate it 90, it would be the highest. We'd say that the 70 scores occurred most frequently, and the 80 scores occurred also fairly frequently, and so on. Okay, and this is called a stem and leaf plot. Okay, so you can go through this. Let's see, what are dot plots? Oh, one other thing, let's just read what the definition is. Stem and leaf display of quantitative data. Each value is divided into 2 portions, a stem and a leaf. So I guess this is called the stem, and these are called the leaves over here. The leaves for each stem are shown separately in a display. Okay, well, let's see what dot plots are. Outliers or extreme values. Let's see if we have an example. Okay, let's say, all right, let's look at this. The distances of longest field goals in yards made by American football, something, AFC, kickers during the 2008 NFL, I don't know what that stands for, NFL season. Okay, this is about American football, and instead of meters, they're using yards. A yard is just a little bit smaller than a meter, but you can just think of it as meters. So here we have someone named S, this guy, and his team is Baltimore, and the longest field goal that he made is 54. And then we have a guy named Stover, and he's also from Baltimore, and his longest was 47, and so on. So, like, who had the longest one? This person and this person, right? 57. So, this guy, Janikowski and Keiding. Okay? Anyway, so that's the data that we have. Okay, now we can make a so-called dot plot, which looks something like this. So apparently, I guess there was somebody who had 43. 43. Right? And there were two people that had what? 45. 45 and a 45. Okay, and that's all. Only two people. And one person that had 47, and so on. And so this is a picture called a dot plot. And notice how you do it is if there's one person there, you put a dot there. If there's one person at 45, you put a dot there. And then if you find another person, you add another dot. Sort of the same distance from here to here is the distance from here to here, and you keep going up. And that way you get a kind of a visual picture, a visual representation of the data. And from that also you can sort of tell something just by looking at this. So you can tell that sort of the average is somewhere around here, something like, or maybe around here actually. I guess it's more like around here. And you can sort of see how it's spread out. Okay, so you know that, like, there's nothing way down here, and anyway. And it's not too, like, it doesn't go like whoop and down. It doesn't look like that. Kind of evenly spread out across this whole range, sort of. Okay, so that's called a dot plot. And here's another one. Here's a dot plot also. Now what happens here? There's one that's way down here, so it's really different than the rest of the data. And when it's so different, you might wonder, this is not, probably wouldn't do it here, but you might wonder, is there something wrong? Like maybe this was recorded incorrectly. And if it's really, really different than the rest of the data, then you might think, oh, maybe it was a mistake. So that's called an outlier, because it's outside of the main data. Okay, now what exactly is it? I mean, how do we define precisely what an outlier is? Well, there are different people will say different things actually, but basically just something that's really far away from the rest of the data. So that's called an outlier. So what do they say is the definition for an outlier? Or it's also called, I guess, an extreme value. Values that are very small or very large relative to the majority of the values in a data set are called outliers or extreme values.